Good evening, everyone. My name is Chris Murphy,
My name is Shamir.
and this summer we were working with two other students, Jamin Reyes and Kanique Liebert, and our mentor, Dr. Hu, to use object detection techniques in order to improve physical security.
While working on this project, we had three goals. Our first goal was to learn about different object detection model architectures and test out their pros and cons, their accuracy, speed, and different trade-offs they may have. Our second goal is to learn how to apply open source software such as TensorFlow and OpenCV to perform object detection. And finally, using our skills and knowledge, we want to adjust a pre-trained object detection model to not only detect common objects, but to also detect objects that can pose a physical threat, such as guns, knives, as well as uncommon objects, such as shadows and flashing lights. So, what is object detection? Object detection is a process of classifying objects within a video or image and finding the exact location of the object and how much space that object takes up. Object detection is made up of two tasks: object classification and object localization. Classification is identifying the type of object, and localization is predicting the object location and the bounds of the object. So, how does object detection work? We train a pre-trained model with images and their ground truth labels, and then we let the network make predictions and compare its predictions to the ground truth. We do this 100 times for 1,000 of images and then save the model and deploy it. We can apply these object detection methods to act as a security guard and alert personnel when strange things occur.
Okay, so I think Shamir did a great job of explaining what object detection is and how it's accomplished. Just a little more details is that when detecting objects in videos, you break up the video into images, and then through each image is passed through a series of layers of computations in order to come out with those bounding boxes. If you're interested, come on Sunday and ask us some questions. We'd love to talk more about this. And why is object detection important for cybersecurity? We do so much to protect people's data online, but all that data is stored in a physical location, which is currently being guarded by people. By using an object detection techniques to secure the premise, we can do a better job than humans at detecting objects. Computers don't get tired, humans do. And we can also do it for cheaper because these humans need to get paid for their services, whereas the object detection algorithms are trained once and then they just work. So the two biggest costs to training object detection models is the amount of data required. There's a lot of images that need to go into training an accurate object detection algorithm. And there's also a lot of computation required to train that model to be accurate. There is a technique that prevents this from being a problem. It's called transfer learning. Transfer learning is using pre-trained models, so models that were trained using maybe millions of images and hundreds of hours of training. Those models are now released to the public, which we were able to find on various sources, one of which being TensorFlow Zoo. So you find these models, these pre-trained models, and then you feed the pre-trained model your new data, which is similar to the pre-trained model's data that it was trained on, but slightly different. And then once you feed your data to that pre-trained model, you can then transfer the learning over. And this results in you training your model much more quickly with less compute than if you were to use train your model from scratch. It also leads to higher accuracy than if you were to train your model from scratch. So there's a general process of training object detection algorithms. It starts by getting familiar with the very popular softwares that are being used today to build these models. Some of the popular softwares that are being used are OpenCV, TensorFlow, Google Collaboratory, Matplotlib, and NumPy. We started by getting familiar with these softwares. Then there's some things that follow. To train an object detection algorithm, you need images, and you need those images to come with bounding boxes. Maybe you label the images yourself, or maybe you get someone else to do it. Once you have the images and the bounding boxes, you can then generate TF records, which is the bounding box is stored in a very efficient format for the computer to take advantage of and learn what the true label is, and then try and figure out how that was how to learn to predict that in the future. Once you have the TF records, you can execute a training script using a GPU. You can train a model pretty quickly. And then once you have your model trained, you can export the inference graph and use it on future data. We trained our model using some training data and saved some data for testing. We then tested our models. How accurate were they? How quickly did they produce these inferences or produce the classifications in the bounding boxes?
All right, so our first test was to try to detect shadows. Why shadows, you say? Well, shadows are really unique. You can gather a lot of information from shadows. And also, no one really has done any detection using shadows. So we wanted to be the first, as well as we wanted to see how much information and how useful can detecting shadows be for our data sets. So here in the image, you could see a monster-looking um, shadow, and usually when a camera or regular security systems, they usually just look for people. But if you have a shadow detection model, you can see different, you could tell different stories from the shadow. You can see if they have a gun, you can see have different items, and just detecting the shadow in places where it has bad lighting or the camera cannot cover every single position. These type of detection algorithms are really helpful for improving the security. So, um, how we trained our shadow models were that we gathered a lot of shadow data. So from Stony Brook University, they had over 4,107 images containing shadows and their corresponding shadow mask. On the left, you can see the image, and then on the right is the corresponding shadow mask of the shadow.
So we don't have a model just yet that can detect shadows, but using OpenCV, we can easily draw these bounding boxes from the instance segmentation mask. Once you have the coordinates of the bounding box for each image, you can then write this to a CSV file. And then once you have the CSV file containing the file name of the image, the width of the image, the height of the image, the class, in this case it's just shadows, and the upper left corner of each bounding box and the lower right corner of each bounding box. You can then do this for all of your images, gather it into a training CSV and a testing CSV, turn those CSVs into TF records, and then we're ready to train our model. So when we train our models, we train 4 different models, each starting with a different pre-trained model. And what we're looking at here are the loss that the model got after a certain amount of training steps. So in general, you can see that the single shot detector pre-trained models got down to a loss of about 6, and it took about 50,000 steps. Whereas the faster recurrent neural network model got down to a loss of about 1, and it took only about 10,000 steps. And loss you can think of as basically the inverse of accuracy. So how well was it detecting the shadows in the testing data set, and how close were the predicted bounding boxes to the true bounding boxes? But as we'll see on the next slide, loss isn't everything. Another important criteria we were looking at was the average inference time that it took for a particular model to make a prediction. As we can see with the faster recurrent neural network, its average inference time was almost zero point 0.2 seconds. And that's just not suitable to execute in real time. The other single shot detector models were suitable for real time, although it came with the price of a slightly lower accuracy. So here's our shadow detector in action a little bit. Here's an image containing a shadow, and here's how our 4 different models performed. And it shows you the bounding box that were predicted. You can see that the faster recurrent neural network was going a little crazy. And it's showing you the inference time that it took for this particular image, and also the confidence that the the detection algorithm came up with for each image. And you can see in the lower right hand side, it didn't detect a shadow.
In conclusion, we found out that the signal shot detector, version 2 Coco, was the most accurate out of all the detectors. The fast RCNN was good at regular images, but it was not suitable for real time, and sometimes it produced false positives. 5 out of the 8 models were useful for real-time detection based on like 30 frame per second cameras, and 3 of the 8 were not suitable. And since the shadow detectors had more data and more testing um, time, we were able to see that it performed way better than the weapon detectors. For future research, we intend to um, get more data so we could improve the robustness of our object detection models, and we want to increase the quantity of all the images that we use in our data sets, and try to use more pre-trained models, and also include new implementations of deep learning algorithms.
And there is one last thing that we could try. If it was impossible to gather more data, there is a technique known as data augmentation, which is just basically, let's say you flip an image. Now you just doubled your data set if you flip your images, because it's a slightly different image for the algorithm to learn on, and you have more data now, which could improve results. If you have any questions, please join us on Sunday from 1 to 2, I believe. Or you can email me at christopher.murphy@students.uvi.edu, or you could email Shamir at shamir.smith@students.uvi.edu. Thank you for listening, and please come on Sunday to ask us some more questions.